Hello, welcome to this validation. Today we are going to take a look at a thick-walled cylinder vessel under uniform external pressure. We have done some validations that are kind of similar. I think they have either had temperature on the inside and outside to get a temperature difference, or we've had internal pressure, but we haven't had one with external pressure yet. So we'll go ahead and take a look at that. It is a Rourke and Young example just to make sure that we are hitting validated results or that the program is producing validated results. As always, what we are going to do is analyze for radial stress and deflection. The outside radius should be 10 inch, inside radius 5 inch, external pressure is 50 psi. We're going to use steel, that is to say a Young's modulus of 30E6. The section itself is 13 inches long, and we are using quarter symmetry, as you might be able to see behind this Excel window. And then from there, we will check its radial displacement. And then we also want to look at, we could utilize a normal Z stress tensor, which would be the normal stress in the hoop or circumferential direction is really what we are targeting here. And this will be a linear static analysis. So let's check some of our measurements before we get into the simulation environment. So if I look at the height of the geometry that I have drawn, you can see that that is 13 inches. If I check the inner radius here, we can see that the radius on the inside there is 5 inch, and then the outside radius should be 10. So there we go, radius of 10. So again, outside radius 10 inch, inside radius 5 inch. So basically I drew two circles, extruded them for a length of 13 inches. So let's go ahead and get into the simulation from design in Fusion. We're going to go ahead and select simulation. And as we go into the simulation environment, we can choose our study. This is going to be a static stress. And then from there, we can begin to set up our model. So the first thing, of course, is the materials. So if I just go ahead down, I can either go to the browser, or of course I can go across from the panels. From the study materials, we'll go ahead and select the material. From the pull down menu, well, first of all, under the material library selection, let me make sure that I am just choosing from the Fusion material library. I do have some of my own material library set up. I want to make sure that what I select you are able to select. So again, after having set that, we will scroll down. And I noticed there is a material in here the other day that is just called steel. There it is, which should be pretty similar to what we want. So taking a look at the properties, clicking the properties button, I can see the Young's modulus there is about equivalent to what we want. The problem definition said a Young's modulus of 30E6. This is pretty close to that. So we'll go ahead and utilize that material, and I'll say OK to that. From there, we can do our loads and constraints. So let's start with the loads, why not? And from the, when I choose loads, we are going to select that this is a pressure. And then I'm going to rotate the model around a little bit. That is the shift key holding down the middle mouse wheel. And we'll select the back face of this geometry. And again, it is going to be a 50 psi. And we'll say OK to that. So there's our pressure. We are pretty close to being able to analyze this geometry. We're going to set up some constraints. First of all, again, it was a cylinder, but we have cut through it. We've made a quarter section of it, so we need to have some symmetry constraints. So with this face here, the way we set up the symmetry constraint is to constrain the translation that is perpendicular to that face. And you can see the mini-axis up here. So the vector that's perpendicular to that face is the x. So we'll select that face and add our x constraint, and we'll say OK. And then over here on this face, we'll do a similar thing. Go to constraints, select that face. The vector that is perpendicular is z. So I will uncheck ux and uy, and we can constrain our z there. So that is the other symmetry face. And then at the bottom of this model, we can constrain it, and there I'm going to do a y constraint. y vector is perpendicular. So unchecking UX and UZ, we'll select UY, and we'll say OK. At that point, I think we are ready to solve it. So I'm going to go ahead and click on Solve. And as always, you have the options to solve on cloud or locally. This one should be pretty quick. Let's choose locally. And we'll go ahead and solve that. Note that I didn't mesh the geometry. I'm just going to let the program use its default, and then I'm going to show you how we can refine it a little bit from there. So as we get into the results environment, let's take a look at what we have. So we can see that you can see the wireframe, the undeformed shape, and the pressure pushing from the outside has pushed it in. And of course, it kind of elongates upward as a result of that load. So let's take a look at our displacements. And we want to take a look at a radial displacement. Maybe it's best if I go back into this orientation. So I can say, take a look at the X displacement on this edge, for instance. So let's take a look at an X displacement. And it doesn't look too bad. If I wanted to get a little bit more precise, I can add a probe. So I'm going to do a point probe. Now with a point probe, let me move it right about there. You can be precise with the placement of a point probe. So I know what this inside corner, the dimensions of it should be. So that one would be -5 in the X. In the Y, we can use 0. And then in the Z direction, 0. So again, that's kind of the point of the point probe, is that you can put in the X, Y, Z coordinates of that probe so you can get it specifically where you want it. So having that point probe on there, I can see what that displacement is. So it's 2.187 e to the -5. So let's say minus 2.187 e -5. And we're about 1.5%. And then we're going to take a look at, we also want to take a look at the stress tensor in this direction. And I am choosing the inside corner here away from the free end of the model so that we can get away from the effects of that free end. So let's take a look at the stress. And again, what I want is a hoop stress or circumferential. So the Z is perpendicular to this edge. So you can imagine the hoop stress, right, at this point right here that is aligned with the XY plane. This point, well, actually all the points on this face here, the Z is normal to it. So that would be equivalent to our hoop or circumferential. So let's take a look at the normal Z. And that gives me a value of -132.8. So we'll just enter that in, -132.8. There we go. And we can see that we get a difference of 0.39. So I think both of those values are quite good, and we could be happy with that. I think that shows that the program is producing what it should be. If we want to refine this model a little bit, that is, since this was a quick model, that is something I wanted to show you. We can do that real quick. Let's take a look at the mesh that we have on the model. So it's not bad. Maybe we want to go a little bit finer. So there's a couple different things, or a few different things that we can do for that. So let me go ahead and say finish results here. And the first thing I'm going to do is just refine the overall mesh. So when I come back into the simulation environment where we do the setup here, under mesh, we'll click the pencil icon. And then I'm going to use a absolute mesh size. So when I click on absolute mesh size, then I can tell it what size I want that mesh to be. And actually, we're going to use a mesh size of 2 inch. Say OK. Now let's generate that mesh. Right click on the mesh and say generate mesh. And that's actually going to take us to a coarser mesh than what you just saw. And then now you can see that we have maybe 3 or 4 elements across the width of this. What I wanted to show you was that you can also add local refinement within Fusion. So if I go to the Manage pull-down menu, under Manage we can go into Local Mesh Control. And we can select faces or edges for refinement. We can also select bodies for refinement. So if we have an assembly, we could select an individual body or several individual bodies and show what that refinement is, or add refinement to those bodies. In this case, I just want to refine this face, right? This is where I am picking up my displacements and my stresses. You can see there's dots on the model that indicate what the current mesh size is approximately. Let me go ahead and select this face, and we're going to use a mesh size of 0.25 inch. So you can see how much finer that mesh will be on that face. So I kind of like that preview. Let's go ahead and say OK. I'll right click, say generate mesh. Notice the exclamation points on the results. So it's saying that the results no longer match the current model, right? Because I changed the mesh up. So that would yield different results. So that's indicating to me that we do need to rerun the analysis, which we can do. We'll just solve. And again, I'm going to solve it locally. Should be a nice quick analysis. If I expand the details there, we can see how it's going. It's already through the point where the contacts have been generated. Really, it's a single part, so on and so forth. So now we're back into our results. And you can see that we have a value of minus 132.7. So I did refine it on that face, but that actually is a little bit further than what our theoretical value should be. And if we take a look at the displacements, let's compare that with our spreadsheet. That also goes a little bit further. So even though we refined that face, because I took it to such a coarser mesh, that moves our results a little bit further away from what was ideal. So we can do one more run. Let's go ahead and finish the results. Let's go into mesh. And let's say we set an absolute mesh size of around 1/2 inch. And we'll generate the mesh. So it doesn't hurt to play with the results or the setup of your model a little bit. So there's the mesh on that. Again, we went from a 1/2 inch down to a 1/4 inch on that refined surface. And it's probably actually a good idea to run several different mesh sizes, right? You notice between those two, I didn't improve the results of my model anymore, but those results were very similar to what we had in the first run. So that gives us a little bit of, what do you want to say, additional confidence in the results that we're getting out of the model. That is, when I change the mesh size, I'm not seeing drastic changes in what my output is. So generally, when you hear about mesh convergence or converging upon your results, you would do 3 different runs in order to make sure that your model is converged pretty well. All right, there we go. So there we are taking a look at displacements, 2.189. I'll leave that right where it is. We'll say it's right about 1.58. Why the heck not? We'll put it in 2.189 E minus 5, and that gives us a 1.49% difference there. And if we take a look at our stresses, let's go ahead and take a look at that stress tensor. And there we go, minus 133.2. So that does improve the stresses there, 133.2. And that gives us a percent difference of 0.09%. So a very small difference compared to what the theoretical solution is. So I think that's a really nice validation for Fusion. Another model which shows us that we are getting out of the program what we expect once we do the proper inputs. So just to finish up, the last thing that I was saying about that is when you do work on a model, you do one mesh and that gives you a result, correct? And then you do 2 meshes and that's going to give you another result. But chances are, I would say, except in very few cases, those 2 different meshes are going to give you 2 different results, not necessarily the exact same result. And the question I get a lot of times is, well, which one is correct? It's a little bit hard to tell unless you have done a hand calculation and know exactly what that value should be. If you know what that value should be and that's what your simulation tells you the output is, then that's great, right? You've matched what the hand calculation should be. But in a lot of cases, we don't have those hand calcs available. Either it's really hard to do or just haven't gotten around to it yet. And in those cases, if you have two different meshes and two different results, then it's really hard to tell, right? You might not know which one is actually closer to the truth. And so that's why I would say at least three different meshes, and then hopefully by that you see a trend, right? So between your first mesh, you get a result, and your second mesh, you get a result, but it changes. And then between your second and your third result, if you are decreasing the mesh each time, hopefully what you are seeing is, it's converging upon a solution. That is the change in the amount of, or the degree of change within results from mesh to mesh is getting less and less, indicating that you are getting closer to the solution. So anyway, I think those results for Fusion came out really nicely today. Hopefully you learned something interesting, and thanks for watching. Have a great day.